It's truly my pleasure to introduce Professor Maciej Dunajski, a fellow of Clare College and a professor of mathematical physics at DAMT at the University of Cambridge. Professor Dunajski is joining us here as one of the UK Lebanon Atiyah Fellows. This is a scheme that was initiated a few years back, primarily in collaboration with the London Mathematical Society and CAMS, and it's meant to fund or support the travel of scholars from the UK to Lebanon, then from Lebanon to the UK. The scheme was put together to honor the legacy of Sir Michael Atiyah, a long-standing supporter and mentor of CAMS for sure, and one of the leading mathematicians of the 20th century, with, among other things, connections to Lebanon. Professor Dunajski's expertise is in areas of differential and projective geometry. He's worked on solitons and on problems in the general theory of relativity. He offered to deliver a mini course on the calculus of variations, as well as a broad public lecture on geometry, 4 facets of geometry, he titled it. Lectures and mini course will be delivered in a hybrid mode next week when Professor Dunajski will be joining us here in Beirut. And we're very, very delighted to be hosting him, kicking off a much delayed celebration of the Atiyah Fellowship program, and looking forward to many more visits from him. To be sure, Maciej is no stranger to Beirut, having visited previously and engaged in collaborations and discussions with colleagues here, primarily my dear friend and colleague and the former director of CAMS, Professor Wafi Sabra. Today, Maciej has generously offered to give an online overview talk about the course, to set the students, and I see a number who have joined from physics and mathematics, both at AUB and outside, give them a sense of what to expect, perhaps get them going in terms of readings. I leave it up to him to decide how to go about it. Before giving you the floor, Maciej, I want to make sure to thank my colleagues from the math department here at AUB, particularly the chair, Professor Florian Bertrand, and my dear friends and colleagues from the Lebanese University who were instrumental in helping us formulate how to proceed with this visit and encourage students to take part into our activity. And here I am particularly referring to Professor Fida Al-Shami and Professor Ayman Kashmar. Thank you all for your support. Maciej, we're very much looking forward to today's talk and, more importantly, to your visit next week.
Thank you very much, Richard, for this kind introduction. Can you hear me?
Yes, I can certainly hear you. I guess you've tried sharing screen. Do you need to share screen at all?
That's right. I will share screen in a moment. I might as well start doing it right now. I'm expecting you to see. I'm expecting you to see something which looks like a sheet of paper.
Yes, we do.
Can you see something which appears to look like a white sheet of paper saying Calculus of Variations in Geometry Lecture 1?
Yes, we do that. I'm also sensing that the audio is a bit choppy. So I'm going to turn off at least my video, but this may be a problem moving forward.
Okay. I mean, audio is choppy, right?
Yeah, it's a bit choppy, but it's okay. We can hear you reasonably well if you speak slow enough.
Well, listen, I've joined with two devices, and my practical problem, or not really my problem, but the world problem is I'm staying in a house now in Poland with lots of refugees from Ukraine, and everybody uses internet. So I apologize for for slow internet. If it's really bad, the audio is bad, I can join with one device rather than two. You will not see me, but you will see my screen, and that might work.
Now it's perfectly good. So let's proceed. Thank you very much.
Good, very good. Well, let me kick off. Well, listen, I'm delighted to be able to give this course to you, to share the subject with you, and I look forward to my visit next week when I'll be giving this course, proper in person with blackboards, hopefully. And
now we've lost the audio.
Well, you will. I'm with one device, so you will not see me, but my writings. I'm going to give you today an overview of what I'll be discussing in my mini course. It'll be a self-contained 6-lecture course. I'm going to also prepare a set of problems for you, for the students who want to solve it. Go through some practicalities, and we know that the only way to learn mathematics really is to be solving problems. So there'll be a set of problems for those who want to be solving them. And the title of the course is Calculus of Variations and Geometry. And today I'd like to tell you a bit about the history of the subject and to motivate. Jihad, please do interrupt me and tell me if you lose vision. I'm assuming that you see what I'm writing.
Yes, all is fine so far.
Very good, very good. So you see, unlike many, if not most, branches of mathematics, calculus of variation can be traced back to a particular year, particular event, and the year is 1696. And one of the players is Johann Bernoulli. He came from a family of mathematicians. There are many famous Bernoullis. Now, at the time, one way to do mathematics was to set mathematical competitions, so to challenge the contemporary mathematicians to a set of problems, solving problems, and that's what Bernoulli did. He posed a problem, and he advertised it, publicized it worldwide, as one did at the time by means of sending letters, and he expected solutions. I'm going to tell you what this problem is in a moment, and in due course, you'll see that calculus of variation is really a method conceived to solve this particular problem. The legend has it that the solution Bernoulli himself gave wasn't his, but his brother's. It was stolen from the brother, proved to be wrong. And there are many uncertainties and anecdotes to do with this particular problem and competitions, but without dwelling on those too much, I'm going to tell you what the problem is. So it will be a motivating example, which I'm going to call 1.1. I'll be numbering my examples by sections. And it goes under the name of the brachistopher problem. And the problem is this: a particle slides on a wire. So there is a wire on the plane, and it slides on the wire under the influence of gravity. Between two fixed points. Call these points A and B. And our objective is to determine the shape of the wire, which gives the shortest travel time, assuming that the particle is starting from rest. So which shape gives the shortest travel time starting from rest? Okay, let's draw a diagram, a graph. So I'm going to place the wire on the plane, and the plane will be the XY plane with coordinates Y going up and X going to the right. And let's say that the particle starts here at point A. So point A has coordinates 0, 0, and the wire stretches on that plane between A and B. And B has coordinates, B has coordinates x2 and y2. So my x1 and y1 are both 0. Okay, and you know, for any given shape of the wire, we can compute the time. I'll tell you how in a moment of this travel. So perhaps the wire looks like this, or maybe it's best to have it looking like this. But what we expect to be true is there to be some optimal shape of the wire. We don't know if there is one, but we would like to find one such that traveling on this wire, the particle will reach B in the least possible time. Okay? So the problem is to find this shape. That's the problem Bernoulli posed. And there are, you know, as many approaches as mathematicians. They and the story has it that one solution has been submitted by an anonymous mathematician, but Bernoulli looked at this and he recognized the genius, the method of Newton, and he said, proverbially, he said one can recognize a lion from its paw. Newton's solution was not variational in the way we're going to describe it. So let me do the following. So it will look like, you know, I don't know what your background is. Some of you are physicists, some of you are mathematicians, some of you are pure mathematicians without any knowledge of physics. For this particular example, I'll be using some concepts from physics, energy conservation, whatnot, but don't be put off by it. I mean, as you'll see that most of the course, the rest of the mini course will be more mathematical, geometric in flavor. So what's the travel time? Well, capital T would be an integral between points A and B of dt. And let's be specific, how do we compute this integral? Well, no, the time for a constant velocity motion, time is the same as the distance divided by the velocity. So that's true at the infinitesimal level. We can therefore say that this is an integral from A to B of dl, where dl is the length element of the curve defining the wire, over velocity, and this velocity depends on the point. So velocity depends on x and y. Well, to make further progress with this, let's use the most important profound laws of physics, the energy conservation. And in this case, we need to keep track of the fact that the kinetic energy of this particle and the particle slides down, see, and the potential energy is a constant. So starts at rest and then moves down, so loses some of the potential energy but gains kinetic energy. Kinetic energy plus potential energy is a constant. Well, the kinetic energy is a half times the mass of this particle times the velocity squared. The potential energy is, well, the height is measured by the y direction, so it's mass times the gravity of the Earth, constant, times y. And this is equal to the total energy of the particle as the starting point, which is A, but at the starting point, the particle, didn't move, so has zero kinetic energy. And we're choosing our reference frame so that the starting position has y equals 0. So the potential energy is also 0. So that's 0. Well, algebraically for the velocity, we get that the velocity is 2g times a square root of minus y. And we're not worried about minus y because we're not worried about taking a square root of a negative number because our y-axis goes up. So there can be action, the motion, if you like, takes place for negative values of y. Well, this we substitute to our formula for the travel time. And now this travel time depends on this function y. Whatever function y of x we choose, that will change the travel time. And it is 1 over square root of 2g times an integral from 0 to some point x2 of the length element. So dl is a square root of dx squared plus dy squared. I can write it as a square root of 1 plus y prime square dx, that's the line element, divided by the root of minus y, so dividing by velocity. Now, our objective now is to minimize this. Subject to the wire having fixed ends. So we're allowing y to be any function as long as y of 0 equals 0 and y of x2 equals y2. Okay, so this is, I haven't solved this problem for you, haven't told you what y is. We haven't got, the tools to do that yet. But this way of setting up the brachistrophe problem leads to a problem of minimizing an integral, and this integral depends on a function which you don't know, and your objective is to find this function. So this is one sort of problem we will solve in the course. Let me give you another example of a variational type problem. And that one is geometric, very basic way, geometric in nature. We'll be interested in finding a geodesic. So what's a geodesic? A geodesic is a shortest path of shortest path on the surface connecting 2 points. Let me call this path gamma. Between
Maciej, we lost you briefly. I don't know what you were saying.
am I back now?
Yeah, you're back now. Yeah.
Where did you lose me?
I must say that the audio is a bit choppy again, Maciej. I'm sure we're experiencing difficulties with the internet.
Let me try ask you to hear the intro. I'll be back. The second variation of problem, I mean, leading mathematics would developing is that of finding a geodesic, which is the shortest path exists. Now, for simplicity, now let's assume that this surface is a plane, a Euclidean plane where the Pythagoras theorem holds. So, you will not be surprised by the answer. Most of you all know that the shortest path joining 2 points is a straight line. But let's assume for a moment that we do not know it. How would we aim to set things up? Again, start with the XY plane. Pick 2 points A and B on the plane. B has coordinates x2, A has coordinates x1, and then y1 and y2. And these 2 points connected by many paths. For example, one of these, but trying to change my color, amongst all these paths, there will be one which is shortest. And that's the straight line. How would we find it? Well, we need to contemplate the distance between the 2 points. And this distance depends on the function we use to draw a curve connecting these 2 points. So it's an integral from A to B of the line element. And this is an integral from x1 to x2 of, well, 1 plus y prime squared dx. And the geodesic problem would be seeking to minimize this d by varying all possible paths lambda and looking for a minimum of d on the space of paths. Right, so these 2 examples illustrate what sort of mathematics we will need. So now let's move away from these 2 examples, talk about general, what connects them, what's the general concept, so mathematics. We will aim to be minimizing or sometimes maximizing objects of the form capital F of y, which are integrals between 2 points of some given integer f of y x y prime dx. Let me give this number, that's 1.1. And we will do it amongst all functions y of x such that y of x1 equals y1 and y of x2 equals y2. Now, what sort of object 1.1 is? It's not quite a function, it's what's called a functional. 1.1 is a functional. So what's a functional? Well, informally speaking, a functional is a function on the space of functions. So, what are functions? Well, a function is a prescription which, giving a number, gives you another number. That will be function on a real line. For a functional, the input is a function instead, but the output is a number. Well, one simple example of a functional is computing the area under a graph. So if we, for any given function on a real line, draw a graph of this function between 2 points, x1 and x2, and then to this function, y of x, we might want to associate the area bounded by the graph of this function and the x-axis. So y of x is mapped into the area under the graph. Now, let's look back at 1.1. What would be this little f in this case? Well, in the case of the graph functional, the little f is just y in 1.1. Another example, that's the first example of a functional. The second example of a functional, take a curve. And this curve can be given to us by a graph function. And to this curve, we want to associate its length. It could be a length of a curve if the curve is closed, or a length of the curve between 2 points. What is little f in this case? Well, it comes from the length element, and it's 1 plus y prime squared. It's what you get by writing as square root of the x squared plus the y squared and thinking of y as a function of x. So with this set, we can then define what's meant by calculus of variations. The subject is to find critical points, extremas, so they can be minimas or maximas or saddle points of functions. Right. So I gave you two motivating examples. I told you what I decoded one of the passwords. It tells me that my internet is unstable. Jihad, am I audible? Can you hear me? Jihad, can people hear me?
Can hear you reasonably well, Maciej.
Oh, good, very good, very good. I was just, reality check.
Sure.
Back to my screen then. What will I do in this mini course? The first lecture, this is the first lecture proper on Tuesday, we'll be finding some necessary conditions for a functional 1.1 to admit an extremum. This will lead to what's called the Euler-Lagrange equation. This will be followed by loads of examples. Mostly from geometry. So I'll talk about things like soap films or soap bubbles, which for a mathematician are minimal surfaces. Now we will finding given some boundary of a surface, how do we, or maybe two boundaries, two wires, how do we find a surface joining these boundaries which has minimal area? We will also give a variational setup for the simplest non-Euclidean geometry. So we'll discuss Euclid's axioms and see what happens if we take away one of these. And see by variational methods there exists a geometry which satisfies the first four Euclid's axioms, what they are, but not the fifth one, and how to find geodesics in this geometry. What's regarded as a very more advanced topic, but I think within our reach, we'll talk about the second variation. So this is an analogon of a second derivative. You see, if a derivative of the function vanishes, you know that this function has a critical point, but you don't know about the nature of this point. You need to investigate further. Well, that's far more complicated in calculus of variations, but it can be done to some extent, and that's what I'll tell you about. So there we'll discuss some sufficient conditions. And depending on how it goes, and I'll be prepared to, in fact, I'll encourage you to interrupt me and ask questions. So I don't, I'm going to get to the second variations. I don't have that much to cover. Time permits, I'll discuss a fairly recent development. There's been a problem in calculus of variations and geometry proposed in the late 19th century, sitting there for over 100 years, which has been solved recently, but with three methods. So I'll tell you about this problem, as close to metrosability problem. He was the guy who proposed it in 1889. This would be some application of the methods we've developed. So that's my plan. Course, and hopefully this lecture. I apologize for this internet interruptions. The lecture gave you some sense of what the course is going to be, but I look for.
We seem to have lost Maciej again.
You cannot start the Jihad. I'm back.
Yeah, we had switched off your video to improve the audio.
Oh, good. Okay, you can turn it off now if that's okay, because I stopped sharing screen.
Yeah, Hiba, you want to? Yeah, thank you. Okay, please go ahead.
Hi there. Well, I don't know where you lost me. I hope you've lost me only a moment ago. So I've listed my last kind of slide was I listed the topics I'll be discussing in the course, finishing with that one of Roger Liouville. Did you get that?
Yes, this came across reasonably well. Yes.
Very good. So I should also say that during my visit to Beirut, although I'll be based in AUB, I'll be very happy, delighted, in fact, to talk to anyone in person about this course or any sort of mathematics they're doing. But I'm also prepared to answer questions now if you have any.
Sure. Any questions from those who have joined us? Either through the chat or by raising your hand, I can try to recognize you. Okay, I don't see any questions. Anything you want to add, Maciej, before I flash the poster of your talks and remind people of the dates?
Well, not really. I mean, I should. I mean, you might say too. I should say that this colloquium will be much more elementary than even this lecture. In fact, it will be elementary to a level that will make it accessible to non-mathematicians. So you regard it more as fun than education, but it will, and that was part of the plan. It will be linked to the course in that the things I'll be talking about during the colloquium at the popular level, we will actually see how they are derived properly using this calculus of variations.
Great. And did I understand correctly that your colloquium will be partly based on your recently published book on geometry?
That's correct, but I don't want to do any hard sale here, Jihad. At least not at the moment. Okay. I'm going to bring a couple of copies with me to Beirut. It's a popular book about geometry.
All right. I can speak for myself and others and thanking you for taking the time to join us from Poland for this overview, preview of what is coming. We're very much looking forward to your visit, Maciej, and to the course and certainly to the lecture. And as Maciej mentioned, please feel free to approach any one of us, myself, Hiba, Hamoud, our officer, or Maciej directly about arranging for visiting with him, chatting with him, and we will also try to visit campuses here in Lebanon, the Lebanese University for sure, but perhaps also colleagues working in differential geometry at the NDU. Very much looking forward to that. Now, before concluding, let me try to flash the poster, and just walk you through the timings of things. So these are the topics for the course that Maciej just went through. So today's was the virtual introductory session. Next week, starting on Tuesday, we will have the first lecture from 12 to 1 p.m. Beirut time. Again, this is a nicely halled room 211. Note that the lectures will be delivered in hybrid mode, so a live audience is of course welcome, and those who cannot join can follow us through Zoom. Then it will be followed by a 2-hour lecture on the 20th of April, which is next Wednesday. Then another 2-hour lecture from noon to 2 p.m. on Thursday. Okay. As to the colloquium, it's titled The Four Facets of Geometry, and it will again be delivered in hybrid mode with live audience welcome at College Hall Auditorium B1. And this is going to take place on April 19th at 4 p.m. Okay, so that's just for the timing. And if you want any additional information, please don't hesitate to contact us. Okay, so thanks again for joining us. Thank you, Maciej, for this wonderful overview, and safe travel to Beirut. Look forward to meeting you in person.
My pleasure. I'll see you on Tuesday before noon.
Excellent, excellent. See you all. Bye-bye.